All right, good afternoon, everybody. We're going to go ahead and get started with our Section 3 notes. Now, you notice for this one, we're talking about three different learning goals. First one, I can differentiate between the types of chemical reactions by recognizing patterns. I can describe chemical reactions in terms of breaking reactant bonds between atoms, and I can predict the patterns or the products of these same types of chemical reactions. What you're going to notice is a lot of these things are sort of interwoven. They sort of work together, and that's why we can get all three of these things in on this one unit. Make sure you're paying attention because I'm going to give you the pattern that we're going to use to eventually be able to classify each of these types of reactions. We're going to get a little bit of practice at it as well. So let's get started. Now, when we talk about classifying chemical reactions, the first one that we're going to talk about is a synthesis reaction. Now, this is how this is an example, of synthesis reaction. We get solid sodium and chlorine gas form sodium chloride. Now, when we look at the overall picture of things, sodium metal itself is actually very reactive and very explosive when put in water. Chlorine gas is something if you breathe in, it'll kill you. But when they go through a chemical reaction together, they release energy and become something that we can actually use and something our body actually needs. Now, what is our base pattern for finding a synthesis reaction? We're going to say that it's going to be A, whatever element or molecule, plus B, another element or molecule, is going to equal AB. So we're taking the things that we had separate and putting them together on the other side. The big characteristic, we're going to have only one new product. So whether it be two things or three or four or five, the fact that we're coming out with only one product in the end lets us know that it's going to be a synthesis reaction. As we're going through this, make sure you fill out the chart because the chart is going to help you to study and to prepare and make sure you're ready to go. So let's look at our second type of reaction. Next type we're going to look at is called a combustion reaction. Now, combustion reaction, I believe, is actually one of the easiest to deal with. Why? Because three parts of it are going to remain the same. Looking at the example we have here, we have propane plus oxygen is going to release carbon dioxide and water. Some of you have propane tanks at home that you use to grill with. This is the same gas that you're working with. Now, other thing about combustion is that's when things begin to blow up. So that's why it's always fun. What's the base pattern we're going to use here? It says CXHY, which means we're going to have some type of hydrocarbon or some type of molecule that's made of hydrogen, carbon, and sometimes oxygen will be a part of it, plus oxygen gas is going to yield carbon dioxide and water. Notice that just in the example we had up top, the example we have here up top, as well as what we have here, these last three pieces match up. This is going to be the same for every single combustion reaction. We always talk about complete combustion. So, what are the characteristics that we're going to look at? Hydrocarbon reacting with oxygen. Products are carbon dioxide and water. These are great reactions to see happen in person. Not so great when we have to balance them, but they take a little bit longer. It's okay. Now, next type of reaction we deal with is decomposition. When you think decomposition or something decomposing, we think it breaks down. So, one good example we use all the time is hydrogen peroxide. When you pour it on the wound, you notice that it starts to bubble up. That's actually the hydrogen peroxide breaking down into oxygen and water. The oxygen is what you see in the bubbles. The water is what's left on the skin. Now, this is what the equation looks like, and this is the balance equation that we're going to work from. Now, what is our base pattern for a decomposition reaction? We have A plus B, whatever compound, notice we have these things put together, yield or produce A plus B. So we're going to break apart the things that we had together. This may be done evenly, so you may get an element and an element, or it may be several compounds. But the key is here, the characteristic is only one reactant. All reactants are going to be on the left, remember. Now, next type of reaction are a single replacement reaction. When you think single replacement, we're only going to replace one thing in this reaction, and it can go one of two ways. One example that we're going to look at is copper reacts with silver nitrate and produces silver and copper nitrate. This is actually one way that sometimes they will get silver out of different compounds to use for plating of jewelry or household products. Now, when we talk about this reaction, one of the things I want you to notice is that, sorry, I'm going to change to the pen so we can see it. As I pay attention here, notice that I had a metal here, copper is my metal, and it's going to replace the silver. So it's almost like it just takes it and it's just going to boot it out. Now, in the process on the other side, now silver is by itself and copper is here bonded in. Now, none of these are actually balanced yet, so you want to keep this in mind. But in this case, we're only changing one thing. Therefore, double or single replacement reaction. This is the base pattern that we're going to use. We have two main types that we may deal with, depending on if the metal gets changed or the non-metal. What we're looking at here is when the metal gets changed, like our example here. Sorry about my writing. Now, over this side is when the non-metal gets changed. And we're going to see examples of both. Now, characteristic, we're going to have one reactant with that's an element or a diatomic. The other one is going to be an ionic compound. The way that we'll know this, one will have a metal, the other one will be an element by itself. The other one on the other side is just going to flip places. When we have metals that react with acid, we'll form gas. Stay tuned for the demonstration we're going to do for that one. Now, when I deal with single replacement reactions, I have some rules that I have to follow. And I'm going to give you guys a copy of this sheet that you're going to keep for reference. Make sure you don't lose it. It's called the activity series of metals. Basically what it's going to be is it's a list of how reactive the metals are. At the top, starting off here with lithium, this is going to be our most reactive metal. Oops, sorry. While gold is actually going to be our least reactive metal. The only way that a reaction will take place is if the metal that is trying to replace the one that we had out front in the previous example is higher on the list than the one that is trying to replace. One person explained it like this. If you are in a relationship with a young lady and a guy comes and he wants to try to get into that relationship, he wants to try to take your girl, he usually has to have something that you don't. That being the case, he would be more reactive, or he'd get a better reaction than you would. But it's only just like switching places in terms of reaction. Now, we have the same thing that's going to happen on the other side if we have our halogens or our non-metals that will switch places. This is our order. You notice there's only a few of them. But fluorine is going to be the one that is the most reactive, while iodine is one that will react a lot less likely. If we have a situation where the metal that's trying to replace is lower on the list, or the halogen is lower on the list, you get a chance to write no reaction, which makes things so much easier to work with. Now, we have still one more type of reaction to deal with, and that's called a double replacement reaction. Now, one example we have of this is silver nitrate and sodium chloride. When I mix these two things together, originally the solutions will look clear, or mostly clear. But when I mix them together, one of the things that you're going to notice is I'm going to start to form something. If you look right here, you notice that everything says AQ next to it except silver chloride. It says there's a solid. This is that precipitate that we talked about. Remember we talked about the fact that I'll mix two things together that were both liquids and all of a sudden this solid will form. That's what we're looking at here. Now, when dealing with a double replacement reaction, it is just what you think. Single replacement, we replaced one thing. Double replacement reaction, we're going to switch partners. So if you notice, we have AB plus CD. On the other side, the metals stay where they are, and the non-metals just switch. That's why we have ADCB. Okay? All we're doing is switching up the partners to form new compounds. Many times you're going to see that we have some type of solid that forms from this. Keep that in mind. Characteristic, both reactants are going to be ionic compounds, and guess what? Both products are also going to be ionic compounds. Ionic just means that we have a metal involved, and so we'll talk more about that later in the year. Usually going to form a precipitate. Now, this is just a general summary of what we just covered. Everything you need to finish off this last part of the unit is right here in this table and with the examples that we're going to do in class. Make sure you pay attention and get all of your notes together so we don't have to worry about anybody missing out or not being prepared for this test. If you have questions, please write them down. Write them down so that we can get them answered in class. If you have any other questions, feel free to email me. We have plenty of practice ahead. Have a great evening. I look forward to seeing you in class.